Hi. In typical Adam fashion, I walk away from something and manage to think of something that I didn't test or need to look at again. And the jump instruction is no different than what normally happens with me. So it turns out, and I'll show you this, that the data that I was testing with was formed in such a way that I couldn't determine which instruction was actually being read. Was it the instruction after the jump, or was it the proper instruction at the jump target? And so today I'm going to get into that, make a determination if that's working correctly or not. And then if it's not working correctly, let's get it fixed. I'm recording this intro ahead of any work, so I honestly don't know if this is going to be a quick video or a rather long one. Let's go find out. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Okay, let's start by illustrating what the concern is here. Here I've got my program counter, and I still have the code in it that I use to test the jump instructions. So when the LED progresses all the way to the end here, like it is, what it's going to do is it's going to jump back to the beginning, which is address 0. And as I step my way through this, it's basically half of the Larson scanner, and you can see the LED progressing its way up the chain here, if you will. When I get near the end here, this here down on the memory at bus 1, this is the jump instruction that's going to get executed. So that's going to get loaded here into the fetch register. This is the target of the jump instruction, but you'll notice I have one past what that instruction is here. Let me interrupt me here to clarify something. This is not one past the instruction. This is actually the jumped target. The contents of that memory is 0, which is the actual target. And the address of that target is 2-1. Now keep in mind that in my architecture, every address is actually shifted to the left by 1 bit, such that I have a 17-bit address and the least significant bit is always 0. I'm always reading a 16-bit word. And so at address 42, that contains the target of the jump, which is 0. So I'm not going one beyond where I thought I should. Now let's jump ahead to where I'm actually accurately describing what's going on again. So when I move this up into the instruction register, the target gets moved here. My program counter represents the correct instruction. My memory bus 1, which is coming into the fetch register, so we'll call it the fetch bus, has the correct instruction in it. But did it come from the address that was here, or was it the address that was the target? That's what we needed Architect to test for today. Okay, so to change this test, what I really need is I need to have something different than a move instruction to register R1 in this position here when I perform this, right after I perform this jump back to address 0. So when I assemble this and I roll back to address 0 here, the target of the jump instruction being 1-3 is now different than the instruction immediately following the jump back to address 0. So here's the jump to address 0, and then now I've got something that is completely different than my target. That means that when I perform that jump, I'll now be able to discern the difference between what is being executed and what's not. I could have put a no-op in there, but I didn't want to confuse the no-op with the instruction here, or the jump target here, just to make sure that it was distinct from either of those two possibilities. At the same time, I made a change to the assembler. I'll make sure that this is available on GitHub for you. And to look at that, it was a relatively simple change, but the purpose of the change was to suppress the disassembly when I had something that required a parameter, if you will, that was in the instruction stream. So in other words, if I come up with something that's moving to a R1, a value that is the next word in the instruction stream, I suppress the output of the disassembly for that. And that was a relatively simple change. Like I said, this will be available on GitHub by the time this video is posted and available to you, so you'll be able to see that. Similarly, the test code will also be available on GitHub. Let's write this to an EEPROM and give it a test. Okay, I've burned my new program onto my memory EEPROMs, and let's plug this in and give it a test. So reset here. Okay, so there's the first move, second, and we'll go all the way through this. There's my jump instruction, which is now moved up here and latched. This is my jump target down here. So that's advanced. There's my jump target, and this is my fetch from address 0, which is a move instruction. So that's 1-3 being that move. Recall that I put a different jump in that position immediately afterwards. So this works exactly the way it was supposed to, and my concerns have been addressed. Well, that certainly worked out better than I was anticipating. I honestly thought the fetch register was fetching the wrong instruction. But I can't argue with success, so I'm going to accept the win, and so this ends up being a very short video. In the next video, I am going to look at the ALU design. This is a critical component in the architecture to make sure that I'm actually getting the performance I need out of it. I do want all of the ALU instructions or ALU related instructions to be a single clock cycle, if I can do that, which means I have to flatten the ALU out as much as I possibly can. So in the next video, I'll tackle some of the design aspects of the ALU that I need to put together, and we'll start laying the foundation for that. Thank you. We'll see you soon.